Start with vapor cycles. In this case, first we'll consider the Carnot cycle, which is supposed to be the ideal cycle for all power plants. Then we'll go for Rankine cycle, that is simple Rankine, and then we'll see the modification of Rankine cycle. 4 processes. So in TS plot we can show this. This one is a dome. Cycle can be represented in the state from 1 to 2. 1 to 2 is the wet steam is compressed isothermally. Then from this process is 2 to 3, then 3 to 4 and 4 to 1. This one is 1. This temperature we called as high temperature and this one we called as low temperature. The Carnot cycle is essentially consists of 4 processes. This 4 to 1 is isentropic process. 1 to 2 is isothermal process. 2 to 3 is also isentropic process. 4 is also constant temperature process. Here S1 is same as S4 and S2 is same as S3. So 4 to 1 is isentropic compression, 1 to 2 is isothermal expansion, 2 to 3 is it a isentropic expansion and 3 to 4 is a isothermal compression. So heat is added at a constant temperature Th and the heat is ejected at constant temperature TL. QH, which is normally given by Tm multiplied by delta S. If we have a constant temperature and we know the delta S, that is this one is delta S, so Tm multiplied by delta H. For QH your delta Tm equals to what? Th. So this one is Th multiplied by delta S and the heat rejected will be represented by QL. Is again the same formula Tm multiplied by ds, but this time TL multiplied by delta S. So this area below the 3,4 is the heat rejection and area below the 1,2 is the heat addition. So cyclic integral del Q net heat supplied minus heat rejected and blue net heat supplied V equals to QH minus QL upon QH. So QH by QH is 1 minus QL upon QH. So let's substitute for QH. We get a Carnot efficiency equals to 1 minus QL is TL into delta S divided by TH into delta S. It is again proved that the Carnot efficiency is only dependent on temperature. So for any thermal cycle, this efficiency is maximum efficiency and is Carnot. Carnot cycle is not practical because one process is isothermal and other process is what? Isentropic. And we are performing isothermal and isentropic continuously. One process is working at very low speed and one is working at very high speed. So this is practically not possible. Second thing is that from 4 to 1 is a isentropic compression. And in isentropic compression is the point number 4 is a wet condition. Number 1 is saturated liquid condition. So we have the particles of water as well as we have the steam condition. And here this one is 1. So this process to be carried out is very difficult because the water is present here. So you have to avoid this process. Secondly, in expansion also 2 to 3. At the inlet it is the dry and saturated steam and then at point number 3 it is a wet condition. So there is suspended particles of what? Water. If you design the blades to carry out the expansion of gases, then naturally the blades are very thin, whereas the blades which are designed to carry the liquids, they are a little bit thick. So any type of blade that you design for carrying out the expansion of steam will not sustain the momentum due to the water particles. So therefore there is a erosion of the blades. So the first reason is we give the condition at exit of the turbine is wet, therefore blade erosion takes place, that is not desired. We are working at 2 pressures only. One is the high pressure and one is the low pressure. Normally the high pressure is called as boiler pressure and the low pressure is called as condenser pressure. So we'll try to eliminate the problem generated in Carnot and that we called as Rankine cycle. So this device is called as boiler. This turbine, as by turbine is coupled to generator. The function of condenser is to change the phase. It will compress the liquid from low pressure to high pressure. So this red line here indicates the high pressure and indicates the low pressure. This one is high pressure, high temperature steam. This one is high pressure, the liquid. This one is low pressure, liquid. This one is low temperature steam. Process in the boiler is assumed to be constant pressure. The process in condenser is also assumed to be constant pressure. The turbine process is assumed to be isentropic and the pump process is assumed to be isentropic. This is called as ideal Rankine cycle. In the temperature versus entropy graph, first of all we'll fix up two pressure. One is low pressure and one is high pressure. So we'll start with state 1. This one is state 2. This one is state 3 and this one is state 4. In any type of Rankine problem, this condition is always fixed. This one is saturated liquid. The saturated liquid at low pressure is represented by this point. That is, so let assume this condition is equals to dry and saturated. So the state 2 is represented by these 2 points, that is 4 and 2. These are default points and standard points. So 4 to 1 is isentropic process. So you have to move along vertical line. From 1 to 2, this one is constant pressure process. 1 to 2 is constant pressure process. 3 2 to 3 is isentropic process. So to 4, this is a phase change process. Case of HS plot, from this point to this one, it is called as dry and saturate line, that is x equals to 1, and leftward it is called as saturate liquid line, that is x equals to 1. X equals to 0. And in this case we can draw two constant pressure line first. So I will draw this line is a constant pressure line. Call this as P condenser. And then we'll draw one high pressure line. The standard point is here is 4, which is a saturated liquid and is at low pressure. So we can fix up point number 4 here. And other point is here 2, which is dry and saturated but is on high pressure. So we can fix up point number 2 here. And now we will finish up with the two constant pressure process and two isentropic process. So we go back to the pump 4 to 1, the isentropic process. So I will move vertically upward. It's a constant pressure heat addition process. And from 2, that is entry to the turbine to the exit of turbine, is isentropic process. So this one is isentropic process. We close this. This is a dome. So this point is our critical point. This one is dry and saturate line, x equals to 1, and this one is x equals to 0. That is a saturate liquid line. So constant pressure lines here will be the like this. It represents the boiler pressure. The 4 is saturated liquid at low pressure. So this one is low pressure and this is saturated liquid. So this one is point number 4. And point number 2 is dry and saturated. So this one is saturated. 4 to 1 is isentropic compression, and it is known that in the compression volume will reduce slightly. So because of this one, my point number 1 will be slightly leftward. This one is 4 to 1. And 1 to 2 is a constant pressure process. It is also known that the 2 to 3 is the expansion process. And in expansion process, the volume must increase. And in all this figure, I have shown my point number 3 in a weight region. But volume has been increased. So 2 to 3 represents expansion. And 3 to 4, we have a phase change at constant pressure. So these are all PV diagram, TS diagram, HS diagram for a Rankine cycle. All devices are working in a cyclic process, and normally we neglect the changes in kinetic energy because the magnitude of kinetic energy is very, very small, and magnitude of potential energy is also very very small. Is Q plus HI plus half VI square plus GZI equals to W plus HE plus half VE square plus GZE. This is a steady flow energy equation where VI, ZI represents, I represents inlet, E represents exit. And since we are neglecting this quantity because the magnitude is very very small, so you left with generalized equation equals to Q. So governing equation for all these Rankine cycle components are Q plus HI equal to W plus HE. As far as boiler is concerned, the entry is represented by 1, exit is represented by 2. In case of boiler, work is always equals to 0. So this equation is Q 1 2 plus entry point is H1, W is 0 and HE is 2. So Q12 is equals to H2 minus H1. H2 is the enthalpy of steam and H1 is the enthalpy of water. So always this quantity is positive. It indicates that heat is supplied. So heat supplied is, it is just a difference of higher minus lower enthalpy. As far as turbine is considered, we have model it is a isentropic, so value of Q equals to 0. Entry to turbine is 2, so Q is 0, so this one is H2 equals to W, this one is 2 to 3 process plus exit is 3 point, so this one is H3. So W23, H2 is a high pressure high temperature steam and H3 is low pressure low temperature steam. Naturally H2 is more than H3, so this quantity is always positive. We call this work developed by turbine and we represent this by WT. In condenser there are no moving parts, so work done in the condenser is 0. Same equation Q plus HI. Inlet for condenser is 3, is 0, exit point is 4. So Q equals to H4. This one is Q34, H4 minus H3. H4 represents water, low pressure, and H3 represents steam, and it is a wet steam. Naturally, H3 is more than H4. So this quantity is negative. We called it as heat rejected. So this one is heat rejected. That. So I write Q out. Now this, when I write out, means I am confirm the sign. So this time it's a H3 minus H4. So again the formula is straightforward, higher value minus lower value. In case of pump, we have modeled this as isentropy equals to 0. Now we have entry point is 4 and exit is, so entry point is 4. This is equals to W. This one is 4 1 plus exit is H1. Exit of pump is H1. So W41 equals to is water but is low pressure. H1 is water but is it a compressed water, and enthalpy of compressed water is always more than the normal water. So this quantity is always negative. I will write this as pump WP. So I will show the arrow like this. This is W pump. So it will be equals to now H1 minus H4. Whereas my turbine work is positive, so I will say my arrow is this arrow. So this system, that is boiler, is meant for heat supply. Condenser will reject the heat. In turbine we are producing the work, and in pump we are receiving the work. You just go to the figure, identify the component and write higher minus lower. So in case of boiler, higher is 2, lower is 1, so H2 minus H2. In turbine, higher is 2, lower is 3, so H2 minus H3. In condenser, 3 is more as compared to 4, H3 minus H4. And in pump, H1 is more as compared to H4, so H1 minus H4. Forget about this. So the Q in minus Q out must equals to WT minus W pump. That is the first law for cyclic process. So we can very well write cyclic integral del Q. You have to follow the sign convention. This is plus Q in. This one is minus Q out. And for this one, the cyclic integral del W, this one is out, is positive. This one is in, is negative. Internally, all these values are positive. So Rankine cycle efficiency is defined as, Rankine cycle thermal efficiency is defined as same as the heat engine efficiency, which is W net. So substitute for WT, W net equals to WT minus WP supplied. Work required to drive the pump is very small. Therefore, W net is approximately equals to WT. The numerical, it is mentioned that you consider pump work, so you do consider pump work, but it hardly matters to calculate the efficiency. Right, we are going for power. Power equals to power developed by the steam plant. Power developed at this point, that is the net power developed, is simply equals to mass flow rate of steam multiplied by net work. This one is our W dot net. So if you supply m dot s quantity of steam, then you can produce W dot quantity of power. So to produce 1 kilowatt of power, how much steam is supplied is called as specific steam consumption. So if you take a ratio of these two, what we get is SSC, specific steam consumption, divided by mass flow rate of fuel, that is the steam, is equals to 1 divided by W dot net. Only thing that you are always expressing is what? Per hour. So you have to multiply this quantity by 3600. 3600 is a conversion factor from per second to per hour. So SSC, specific steam consumption, is simply m dot s divided by W dot net. The standard value for this one is around 2.5 in case of steam power plant, which is supposed to be, this W dot net is same as m dot W net, and this is m dot s. So is it get cancelled? So what is left is SSC is simply equal to 300 and W dot net is replaced by m dot s into W net. So we have simple formula to calculate SS tag is kg equals to HF, is it at condenser pressure, and suppose if you know the condenser temperature, then you can use Cp of water as a shortcut formula multiplied by temperature of condenser must be in degree Celsius. So we can very quickly calculate the value of H4. 4 to 1, is it a compression? Work of compression in case of pump is given by integral minus VdP, has to be integrated from 1 to 2, is integral minus of V, volume is assumed to be constant for water, specific volume, is integral from 4 to 1, so 4 to 1 is P1 minus P4. So WP will be written as simply as V into P1 minus P4 multiplied by 100. 100 take care of what? Bar to kilopascal, and therefore this quantity will come in kilojoules. So this quantity is H4. So if you draw this diagram like this, so initially you are present with enthalpy equals to what? H4. You are giving the WP, and finally you are available with H1. So does it mean that H1 equal to H4 plus WP by first law, conservation of energy, energy in equals to energy out. So we can calculate value of H1 equals to W of pump plus H4, but W of pump was given as V into P1 minus, take the V, I have to take the V at point number 4. So this one is Vf at condenser pressure, and this condition is normally mentioned to you whether it is dry. If it is dry, then S2 equals to Sg. at boiler pressure, and H2 equals to Hg at same boiler pressure. And if you are given the pressure P2 and temperature T2, it means that the steam is superheated. If the steam is superheated, then if the standard data available, then you can use that value. Otherwise, you can use Sg. Sach is normally provided, and this T2 itself is called as T. And if you want to calculate H2, then it's the same formula, Hg. That is actually T soup minus T sach. So indirectly, if you know the value of T sach, that is they will provide, so you can calculate the value of T soup, and the calculation will remain same. 223 is isentropic is equals to S3. Whereas S2, you are already first find out Sg at low pressure steam. And if this value of Sg, as it indicates this point, is more than the value of S2, then point number 3 will be on left hand side, that is on wet region. So if Sg is greater than S2, Sg at low pressure is this point and S2 is this point, which is Sg for the boiler pressure. So S2 is less than Sg. So you can conclude that Sg is greater than S2, then the 3 is in wet state. Steam from this confirmed result, you can write S3 equals to, at this point, this one is SF, condenser pressure. If the entry to the turbine is superheated, and I select such a point like this is 2, and if I come from this point, I am getting the point number 3 here. So for this case, S2 will be calculated like this, and suppose by chance the point number 3 is here. So in this case, Sg at low pressure, is it lower than the value of S2? So if Sg is lower than S2, you conclude 3 is superheated. So P is same as S2, and S3 is equals to Sg plus. Now this time we are finding the temperature at 3, so I write directly T3, which is in Kelvin, divided by this temperature, that is T sach. All this data corresponds to condenser pressure. We are able to calculate the value of T3, which is basically T soup. Once we know this value, we are able to calculate the value of H3, which is equals to, for superheated steam, state 3 is on condenser pressure.